So now we're going to have a look at hypothesis testing with the binomial distribution. And just as we've had in previous hypothesis tests, this one has a one-tail and a two-tail. So we're first going to have a look at one-tail binomial hypothesis tests. So this time we do not get our critical value from the formula book. Instead, we're going to use the critical value as the significance level in a one-tail test. This is only in one-tail tests. Our null hypothesis and alternate hypothesis are always going to refer to probability, which, as you can see here and here, use a P symbol. You need to make sure that the symbol definitely looks like a P and not a rho, because obviously that was for PNCC hypothesis testing. The null hypothesis will always be that P is equal to whatever the probability in the question states. And the alternate hypothesis will always be for a one-tail test that probability is increasing or decreasing. So P is going to be less than or greater than the value that was given in the question. So a large batch of potatoes is to be sampled for potential frost damage. Out of a sample of 40 potatoes, a random sample of 40 potatoes is selected. 2 of them were found to have frost damage. We're trying to investigate at a 5% significance level the claim that less than 15% of potatoes show evidence of frost damage. So from the question, we know that the distribution that we are using is X squiggle B. We've got 40 potatoes that we're looking at, and the probability that we're looking at is 0.15. And this is that we have frost damage. So then, our H0 is going to be that the probability is 0.15, and our H1 is going to be that the probability is less than 0.15. So other than the significance level, the only value that we haven't used yet is the 2 that we got from actually doing our test. So this 2 that we actually got from doing our test tells us that we're going to be looking at the probability that X is something than 2. And the easiest way to know which way around the symbol goes here is that it's going to be the same as what's in our H1 for one-tail tests. But because we've actually already found 2, it's also going to include 2 when we're trying to find our test statistic. So this symbol here will always be less than or equal to or greater than or equal to. It will never be less than, it will never be more than, and it will never be equal to. It will only be one of these 2 symbols. So then we can put this into our calculator. So we go into dist binomial, and then we go into BCD because it's not equal to. So it's less than or equal to or greater than or equal to, so we're going to BCD. So the smallest that we want is 0. The most that we want is 2. The number of trials that we have over here is 40, and our probability is 0.15. So that gives us a probability of 0.0486. That is our p-value or our test statistic in this case. So what this value tells us is the chance that out of 40 potatoes, if the probability of them getting frost damage is 15%, the chance that only 2 or less of them would have suffered from frost damage just by chance. Now, as I said before, the critical value we get from the question for a one-tail test. So the critical value is going to be 5% as a decimal is 0.05. And you can see here that the probability that we have found that this happens by chance is rarer than our critical value, which means that it's likely that actually the probability is less than 0.15. So as the test statistic is less than the critical value, we're going to reject H0 at a 5% significance level. There is sufficient evidence to suggest the probability that a potato is frost damaged is less than 15%. So just as we have in previous hypothesis tests, we always say accept or reject H0. We always refer to the significance level that we have used for the test. If we reject, we always say sufficient. If we accept, we always say insufficient. And then we always refer back to H1, regardless of if we've accepted or rejected. It will always be the probability of whatever is less than or greater than whatever probability we were looking at. So now I'd like you to pause the video and give the Now You try a go. So hopefully you paused the video and gave the Now You try question a go. So this time we have a train claims that more than 40% of its trains arrive early to their destination. Out of a sample of 150 trains, 73 of them arrived early, and this time we're testing at a 10% significance level. So our distribution is going to be X squiggle B. We're looking at 150 trains and we're testing the probability that it's more than 40. So we're looking at 40, 0.4. And that's the probability that they're arriving early. So then our H0 is that P is 0.4. And our H1 this time is going to be that the P is more than 0.4. So the number that we found was 73. And as I said before, with one-tail hypothesis test, whatever the symbol in the question is, that's going to be in the H1 is, that's going to be the same symbol, but because we've already found 73, we also need to include that value. So this time it's going to be P of X being greater than or equal to 73, which as you can see from a calculator here, if you've got one of the new ones, we can put 73 in the lower, 150 in the upper. The number of trials is 150 and the probability is 0.4. Just as a quick side note, if you have one of the older calculators, remember that to find this probability, we're going to have to do 1 minus the probability of X being less than or equal to 72, and then 72 will go in for your X. So just bear that in mind. If you have an older calculator where you don't have lower and upper and you only have X, here 72 needs to go in for your X. And then you need to do 1 minus that answer. So as I was just saying, that gives us a probability of 0.0193. The critical value this time, because we're using a 10% significance level, is going to be 0.1. So again, as the test statistic is smaller than the critical value, we reject H0 at a 10% significance level. There is sufficient evidence to suggest that the probability of a train arriving early is more than 40%. Now, I've also added this little comment here at the bottom. It's a little bit hard to see because it's in yellow. But actually in the question, they were asking us to investigate the company's claim. Now, if it's ever saying to investigate someone's claim, it's always a good idea to write your conclusions still in the context of whatever you were testing, but then to add a statement at the end as to whether the claim was correct or false. And make sure that you don't make any definite statements. Again, in statistics, it's only that we found that something is probably true or probably false. These could have been 150 specific trains that were looked at. Maybe the sample wasn't random in reality. So we just need to be careful that we just keep it open. So the company's claim is probably true, not that it's definitely true. Now, as I said before, there is also two-tail hypothesis tests. And this time, for the two-tail hypothesis tests, still our null and alternate hypothesis are going to refer to probability. However, this time, instead of us using the critical value as the significance level, the critical value is going to be half of the significance level. And the reason for that being is that this time our H0 is going to be that the probability is equal to whatever the probability in the question was. And our alternate hypothesis is going to be that the probability is not equal to whatever it is that we were looking at. So this time, actually, we're wanting to look at both ends. So if you think about a straight line, we're not just looking at this end and putting all our eggs in this basket here for seeing if it's increased. Instead, we're looking at both ends. And because we want to keep it fair and not look at one side more than the other, if, say, we have a 10% significance level, we're allowing 5% down here and 5% up here. Sorry, it's a bad pen to use to try and write. Just write that again. So we're splitting our 10% between here and here. So if we have 10% to start off with, we are splitting it between the two sides. Now, when we're trying to find the probability, we're obviously not going to look at it being less than or equal to or greater than or equal to. We're only going to have a look at one of those. And to help us to decide whether we're looking at it being greater than or equal to or less than or equal to, we're going to have a look at the mean value. So remember that the mean value is found by doing n times p. Now, if A being the mean, is bigger than the value that we're looking at, then we're going to have if A, which is what we're looking at, is bigger than our mean, then we're going to look at greater than or equal to. And if A is less than our mean, then we're going to look at less than or equal to. So just to clarify, if our x bar mean is bigger than the value that we are looking at, then we're going to have the probability of x being less than or equal to that value. If the value that the mean is smaller than the value that we're looking at, then we're going to look at the probability of x being greater than or equal to that value. So just be careful. We're always seeing if we have more than we were expecting. Remember that the mean is just how many we were expecting to get. So if we have more than we expected, then we're looking at greater than or equal to. And if we have less than we expected, then instead we are going to look at less than or equal to. So this is less than expected. And remember that expected is just another word for the mean in real life context. So, in all these binomial hypothesis tests, the same in any hypothesis test that we use in statistics, if we are not told what significance level to use, we need to be using a 5% significance level. So, we've got a student takes a multiple choice test. There are 10 questions. So we have 10 questions with 4 possible answers. So from this 4 possible answers, we've had a look at a similar question to this before when we were just looking at finding probabilities. Only 1 out of those 4 options is going to be correct. So actually, this is where our p-value comes from this time. So just be careful whether it's telling you how many options there are, and from the context of the question, if only one of them can be true, or whether that's the number that they found when they were doing the experiment. So here we've got, unfortunately, a student has attended very few lessons, and so he's having to guess on the test. The student gets 5 questions right. So that's actually the outcome of our test, that they got 5 questions right. So that 4 there is telling us our probability. The 5 questions right is telling us what they found when they were looking at the 10 questions. So we're trying to investigate whether the student has attained a different result than expected from guessing. So as I said, this time it hasn't given us a significance level, so we are going to be using a 5%. So our H0 is going to be that P equals a quarter. And our H1, well, we're not seeing if they've done better or worse than expected. We're just having a look if they've got different. So we're looking at not equal to 1/4. Now, as I said, we don't know if we're looking at the probability of x being less than or equal to or greater than or equal to 5. We have to have a look at our mean. So the mean is found by doing n times p. So in this case, our number of trials is 10 times our probability of a quarter, which gives us 2.5. So if they were guessing, we were expecting them to get 2.5 of the questions right. However, in reality, they got 5 questions right, so they got more than we expected, so we're looking at greater than or equal to. So then we can put that in our calculator. So the lower is going to be 5. The upper is going to be 10 out of 10 number of trials, and the probability is a quarter. So that gives us 0.0781. Remember that that's our test statistic. As I said before, because this time we're wanting to split it between the bottom end and the top end, that means that our critical value is going to be half of our significance level, which is 5%, which gives us 2.5%, which as a decimal is 0.025. So that 0.025 has come from the significance level, but then halved because it was a two-tailed test. And we're making the same comparison as we did before. So here our test statistic is more than our critical value. So as the test statistic is bigger than the critical value, the chance of this happening just by chance, by luck, is bigger than what we were expecting, what we were looking at. So that means that we're going to accept H0. So then at a 5% significance level, there is insufficient evidence to suggest the probability of the student getting an answer correct is not a quarter. And the reason why we have to put that is that, remember, when we write our conclusion, we are referring to our H1. Our H1 is that the probability is not a quarter. So in our conclusion, we are writing about not a quarter. So just going through another example. So here we've got the probability that a student at a certain school passes an exam is 0.8. So that's our P. A new teacher is appointed and takes the next group. Out of 10 students, so that's our N. So if we were to write our distribution, we've got X squiggle B, 10, 0.8, and that's passing. 9 students now pass. The head teacher is impressed with the new teacher's rate. Investigate a 10% significance level whether the teacher's results are different from the school's pass rate. So again, it doesn't say increase or decrease, it just says different. So our H0 is going to be that the probability is 0.8. Our H1 is going to be that the probability is not 0.8, testing if it's different. Then we need to have a look at the mean. So n times p, so that's going to be 10 times 0.8, which gives us 8. So we were expecting 8 people to pass. However, we found that 9 people passed. So we found more than we expected, so we're looking at greater than or equal to 9. So that gives us 9, number of trials 10 out of 10, and the probability is 0.8. Oops, sorry. 0.376 to 3 significant figures. Now that is our test statistic. Remember that the critical value is going to be half of the significance level because it's two-tailed, which gives us 5%, which is 0.05. And then as the test statistic is bigger than the critical value, we are again going to accept H0 at a 10% significance level. There is insufficient evidence to suggest the probability of a student passing is not 0.8 or 80%. So as I was stating before, you have to be careful. In your conclusion, you're always talking about your H1. If we end up accepting H0, we're always saying that there's insufficient evidence. We can't say, just because we are accepting H0, we can't say that we've proved that it is 0.8. We've just proved that it isn't 0.8. That it isn't 0.8. Remember to always have a look at the mean and then compare it to the value that you're looking at. So in this case, we're expecting 8. We found 9. 9 is more than 8, so we're looking at greater than or equal to. If you get confused as to what side you're looking at, if you draw yourself a little number line, so here's my number line here. So my mean is 8. The value that we have in the question is 9. And because I'm expecting it to be a rare thing that I am looking at, I'm wanting to find the smaller area. So if I was to look at this side here, this is obviously going to be more than half because it's a lot of numbers that are going here. However, if I have a look at this side, it's going to be the smaller of the two sides of the 9, which means that this is the probability that I'm looking at, which is the probability of x being greater than or equal to 9. So if you get really, really stuck, have a look on the number line, put your mean on, put the value that you've got from the test in the question, and then have a look at which part of that is going to be smaller. If you put your mean in the middle, and then put your number on either side, whether it's smaller or bigger. Just another note, same as what we talked about in the one-tail tests. Remember that if you've got the old-fashioned calculator, you would have to change these probabilities so that you'd be looking at 1 minus the probability of x being less than or equal to 8 to put it into your calculator. So I would now like you to pause the video. Oh, sorry, we've got another example. So now we're looking at the tulip bulbs are sold in packets of 56, and we've got a mix of red, yellow and white. And we're looking at a random sample of bulbs are obtained and put into packets. A packet is selected at random, and the number of white tulips is found to be 15. So here we have 15. If they're being sold in packets of 56 and it's a mix, and we're trying to see if it's the claim that 20% of the bulbs are sold in the packets are white, because here we're trying to see if it is 20%, it either is going to be 20% or it won't be 20%. Now in the packet there is 56 tulips that we're looking at. And as I said, we're looking to see if it's 20%. So this is white tulips. And the number that we found was 15. But because it's a two-tailed test, we first have to find the mean. Remember, that's NP, so 56 times 0.2. Just popping that into the normal part of the calculator. So 56 times 0.2, which gives us 11.2. That's what we were expecting, but we got 15. So if we have a look at that number line option again, so we found the mean is 11.2. Putting it in the middle of my line. 15 is obviously more than 11.2. And you can see here that this bit is a smaller area than the rest of that line. So that means that we're going to be looking at greater than or equal to again. So dist binomial BCD. The lowest that we want is 15 out of 56. So the upper is 56, the number of trials is 56, and the probability is 0.2. So that gives us 0.136. That is our test statistic. The critical value, because it was two-tailed, is going to be half of the significance level. So half of the 5%, which is 0.025. So as the test statistic is bigger than the critical value, we're going to accept H0 at a 5% significance level. There is insufficient evidence to suggest the probability a bulb is white is not 20%. And again, we're investigating a claim. The claim is that 20% of the bulbs sold in such packets result in white tulips. Well, because we're saying there's insufficient evidence to say that it's not 20%, that means that the claim is likely or probably to be true. So now I'd like you to pause the video and give the Now You Try a go. Okay, so hopefully you paused the video and gave the Now You Try question a go. So this time we had, prior to joining a coaching course, a netball player scored 45% of her shots. The game following the course, she scored 72 out of 135 shots. And we're investigating a 5% significance level to determine if the coaching course has changed her shooting ability. So our H0 is that it's the same, it's still 45%. Our H1 is that it's not 45% if it's changed. The distribution that we're looking at is X squiggle B 135, that's how many shots she takes, and we're testing the probability of 0.45. In order to determine if we're looking at greater than or equal to or less than or equal to, we have to look at the mean, which is MP, which gives us 60.75. We have more than we expected because 72 is more than 60.75. So that gives us a probability of 0.0318. That's our test statistic. The critical value is half of the significance level because it's two-tailed, which gives us 0.025. So then, as our test statistic is bigger than the critical value, we accept H0 at 5% significance level. There is insufficient evidence to suggest that the probability of scoring is not 0.45, which means that her shooting ability has probably changed. Again, with a little comment there in reference to what the claim was. Just a couple of little notices. So if instead of accepting H0 we were rejecting H0, the only things that would change in our conclusion would be at first that obviously in order to reject, our test statistic has to be less than our critical value. Then we would be rejecting H0, not accepting H0, and we would not have the in, so it'd just be sufficient evidence. We would still say not whatever the probability is that we're looking at, because we're still in reference to our H1. Also, just talking back to just having a look back at the one-tail hypothesis tests, if you are not happy, if I just go back, if you are not happy with the fact that this symbol that we use in order to find the probability is going to be the same as what's in the hypothesis test with one-tail tests, you can still use the same method that we were talking about for the two-tail test. So if we were to have a look at the mean for this question, we would have n, 150, times p, which is 0.4. And if I just pop that in my calculator, 150 times 0.4, and that gives us 60. We have more than expected because 73 is more than 60, so it's greater than or equal to. So if you're not happy, and again, if we have a look at the question before this, here, if we have a look at NP, so the mean would be NP, so 40 times 0.15, which gives us 6. So this time we had less than, because 2 is less than we were expecting. We were expecting to get 6, but we only got 2, so it's less than or equal to. So if you're not happy with the fact that it's going to be the same as in the symbol that we use in H1, then you can use the fact that we're in the comparison to the mean, we have more than we expected or we had less than expected, and that tells us if it's going to be less than or equal to or greater than or equal to. Just to re-emphasise, I have already stated this once, but I do want to state it again, that this symbol here will always be greater than or equal to or less than or equal to. It'll never be equal to, it'll never be less than, it'll never be greater than. Whenever we do a hypothesis test, it's always going to be greater than or equal to or less than or equal to, because we have already found the value that we are looking at in the question. Thank you very much for listening.